Let's start. So I want to speak a bit about, not too long actually, on the magnetic field topology, in particular, braiding of the magnetic field.
Yeah,
Sorry?
Phillippe, can you make it full screen?
Oh, yes, I will. Yes, of course. So yes, I will talk a bit about braided field in the magnetic field in the corona. So how good is that assumption? And that, of course, includes helicity on the sun. And well, here you see a nice plotting from Pater Secchi, who painted this in Rome after looking through a telescope on the sunspot on the sun. And he noted there's a spiral structure around it, which was exceptional, but because usually he just painted things and never wrote something on it. So that seems to be a special day. Okay, so yes, we speak about the active region on the sun. So we use data-driven simulations, 3D MHD simulations, to compute what is happening in the corona. And from a schematic, that would look approximately like here. So the idea is that something happens in the photosphere, which is down here. And due to motions in the plasma, magnetic field is, of course, shifted from one place to the other, right? So you have a velocity vector, you have a magnetic field vector, and if you go to 3D, of course, that gives you a cross product, and that would create a Poynting flux, yeah? And this Poynting flux, of course, can have a vertical component, right? So the Poynting flux, of course, points in any direction, depending on the velocity vector and the magnetic field vector in the photosphere, but usually there is also a vertical component, and that would describe the magnetic energy transport into, let's say, through the chromosphere and to the corona. And fundamentally, I think that this is a general description of how magnetic energy can be transported. So no matter what is the mechanism, if it is waves or not, or disturbances or braiding, all that would be included in the Poynting flux here. So that is what we think builds up a magnetic energy depot, so to say, in the corona. And then, of course, the big question is how the magnetic energy gets converted to internal energy. So that would be the actual plasma heating process in the corona. And that is, of course, sometimes not discussed. When people talk about coronal heating, they talk about how to provide energy, right? So many of that mechanism that have been proposed to be the coronal heating mechanism, they just describe the energy transport. They don't describe the conversion. So the dissipation mechanism, I think, is also very important. And of course, there is some crosstalk with kinetic energy, as you see here in the sketch. So of course, there are mechanisms that convert magnetic energy to kinetic energy back and forth. But once you have kinetic energy, there's only dissipation, for example, through viscosity. But looking at the data, I would say that is a minor mechanism, and at least in our model, I should say, the main mechanism is somewhere here. And of course, we have an idea of what could be this question mark. Well, the direct way to convert magnetic energy to internal is, of course, the magnetic diffusivity, so eta. And then what happens with the internal energy once it is in the corona, there are two ways how to lose the energy. One is radiative losses. So that would mean internal energy is converted to radiation. And because the corona is optically thin, then this radiation is simply lost, like to the space. And on the other hand, in the very generalized view, you have heat conduction also. And because the corona is much hotter than the photosphere, the heat usually flows down, right? Because it goes along the temperature gradient. So the heat cannot, well, it can be redistributed within the corona, but the general heat flow is not into the corona, right? So from the photosphere and from the outer space, you wouldn't have a heat flow. Okay. So what is the braiding mechanism that we want to model? So that is called field line braiding. And Parker proposed this idea in 1972. And I made the sketch here. What you see is at the base, so this Z equals 0 layer, that is supposed to be the photosphere. You may have some magnetogram, as you see here. The black and white dots are the magnetic polarities. There's some active region here below. And then what, of course, can happen is due to the granulation that advects plasma in horizontal sense, because once a granule reaches the surface, it creates a horizontal flow also, at least a component of a horizontal flow. And that would shift magnetic fields to the sides or in any direction, actually, in horizontal direction. And because we have mainly advection of magnetic field in the corona, because plasma beta is large, that means, magnetic field is frozen to the plasma movement. And then what happens is, due to this granulation, creates a random pattern of motions in the photosphere. And then it could mean that foot points of magnetic flux tubes, as shown here, or any magnetic field line, these foot points are shuffled around, and could be that some flux tube or some magnetic field lines are braided around each other, right? As you see here in this plot. And then these disturbances, of course, need time to travel into the corona, so that will reconfigure the field in the corona too. And then finally, what could happen is that if you look such places, either where there is strongly banded magnetic field, or if there is at least some, let's say, shear between the magnetic field, that could lead to reconnection cases where electric currents are generated. And finally, these currents can be dissipated in the corona, because very simply, the coronal plasma has, even though it is mostly collisionless, it has, how can I say so, electric resistance. So that means electric currents would heat the plasma locally in the corona. So that is the general idea as Parker had it. And of course, in this sense here, we see vertical field, but in reality, these are of course closed loops. So on the other end here, you also have some braiding, so that could lead to any kind of entanglement finally. Okay. So this is the actual active region that we can use, for example, for the model. You see there are strong polarities, black and white. You see also there are some additional, other polarities, mixed polarities. Next to the black one here, you find a region with some white polarity. So that was observed in 2007 by the Hinode satellite. And that would be the input for the model at the photosphere. So when we run the model, we compute, of course, all the MHD quantities. That includes density and temperature, right? And with these quantities, like density and temperature, we can compute the actual emission that we would expect from each pixel or each plasma packet in the corona. And when we plot that on top of each other, like you see here, this one, the upper panel here, that is a view from the side. So as you would observe the active region on the limb. And the lower panel here shows the same region as seen from top, right? So what you have is here these yellow areas. This is mainly above the strong polarities. And then we get some high energy emission or high temperature emission, like the iron 15 and iron 12, iron 13 emission that you see here in red and in pink. There you see a hot loop connects between those two main polarities that we have seen. But some loops also connect here to the periphery, which is mainly the region where we have this additional polarity at the side of this main black polarity, where there was some white here, you remember. So we find some hot loops. And what is of course interesting is, if you have an observed magnetogram at the base in the photosphere, you should be able to compare with actual coronal observations, right? And that is what we did. So just to justify or to support the model is correct or realistic, or at least, let's say, the loops are on the right place and have the right height, you can do a 3D reconstruction of stereo data, for example. And what you would find is these circles here from the top view, or from the side view here on the left side. These are ellipses that are the reconstructed coordinates from these intensity structures that we have seen also in stereo. And the main finding is, if you consider that line, that is a field line directly traced from the model, while the circles is the reconstruction from the observed loop. We see that the field line that crosses through the loop, or is in the center of the loop, in the center or at the point where there is the largest emission of the loop, this field line roughly coincides with the coordinates that we have reconstructed from the stereo data. So that makes us confident that not only the loops are at the right place as seen from top, but also the height of the loop is roughly correct. And I must say maybe that this plot on the left side is seen as if you look, so to say, from all the right side here in this second plot. Okay, so and yes, and I should maybe also say that the black part here, that is the model emission, and the circles is the coordinates that we have constructed from the observed emission of that loops. Okay, so that seems to be a good indication that the model produced at least some loops that are realistic, or at least at the right place. And then what we can do, of course, we can look at what is the Poynting flux. And in this case, here in this plot, I show you a view a little bit from the top. So you see there's a semi-transparent layer here, and that layer is at the base of the corona at 3 megameters height. And then what you see is a kind of random pattern above these strong polarities. I will explain in a second why that is. And you have a large area of this bluish color, which means blue here is positive vertical Poynting flux, and red means a negative vertical Poynting flux, so pointing upwards and pointing downwards. So yes, then you could see, for example, there is an almost random pattern of red and blue above the strong polarities, which is here the black region and the white region here. And that, of course, is simply explicable by the more or less random motion of the granules. So as I said, now if you go, for example, to this white part here, you have an upwards directed magnetic field vector, and the velocity vector could point actually in any direction. That gives you a kind of sometimes positive, sometimes negative component of the cross product of the two terms, so of the velocity and the magnetic field vector. And that contributes to the vertical Poynting flux, of course. And because the velocity field is more or less random, that could mean there's random oriented Poynting flux of strong polarities. So if you look at the Poynting flux here, you have one term which is U cross B, and you have another term which is J cross B. And because J is the curl of B, that term is represents some general topology feature of the magnetic field, while this other term represents the pumping through the granulation of magnetic energy. And what I can also say is that this large bluish color here that you see, that is actually dominated from this J cross B term. So that means between those two strong polarities, there you have a high contribution from this J cross B term, and above these strong polarities, there the contribution of the U cross B term is larger. So if you would average now the whole area here, so including some quiet sun, still next to the active region, but rather quiet, as you see from the color, you get an average of actually this field of view with about 1 kilowatt per square meter. And funnily enough, this is about what theoreticians say should be the heating of the corona in average. So that makes us quite happy, because we see that the heating that we have through the mechanism here would be sufficient. And maybe I should say that the colors here actually represent plus minus 50 kilowatt per square meter. So you see there are locally strong enhancements to that number. Yeah, okay. So yes, and maybe I should also say the orange color here, that is the EUV emission from that particular loops. And the lines that you see here, they represent the actual field line that cross through the intensity center of the loop, right? So if you go to the maximum intensity, follow the field, this is what you get. Okay, and yeah, what is interesting also is that the loop here in the core, this one is rooted in, as you see, both ends in bluish color. So that means it has positive vertical component of the Poynting flux. And this other thing, which does not develop really into a loop, we see has rooted one end in a mostly zero but slightly positive Poynting flux, and at the other end it seems to be rooted in a reddish area. So that means it has no strong pumping of magnetic energy into the corona, but mainly the energy is actually flowing down, which indicates red color. And if we look here at these loops at the side here in the periphery, we see also, and if you zoom in, you can actually see it also, but I can tell you, so these loops are also rooted always in blue areas, while the other end here you see is mainly white or transparent. And these loops are actually strongly asymmetrically heated, while this other loop here is symmetrically heated. So that means you have a high emission there, exactly there where the Poynting flux or the pumping of magnetic energy is large. And on the other hand, on the other end of the loop, where there's no such strong pumping of magnetic energy, and by the way, also no flowing down of magnetic energy, as you see, there is no red color, there is weak intensity and weak heating. And what is also interesting about this plot, when we speak about the untangling of magnetic field in the corona, well, here we only plot one field line in the core of the loop, of course, but what we see is, if we look at these field lines, they look rather parallel, right? They don't have, at least these field lines of two separate loops are not entangled with each other. That's what we can say from this plot. But if we go below that surface of 3 megameters here, which means exactly at this point, these field lines enter in the chromosphere or in the lower, let's say, sometimes the transition region is a bit higher or a bit lower, but they enter in the lower part of the atmosphere. And there we see these field lines have much stronger curvature, right? Or let's say they are more edgy. They're not so smooth as in the corona. And in particular, these field lines, they actually reach out here. So they connect to some remote polarities. And that is indeed a consistent feature. So a slight change in the position of the field line would not dramatically change here the connectivity. So therefore, I'm confident this is not a numerical error also. Okay. Now, what we can check then is along those loops, which you see here a bit from a different angle, we can plot the helicity density. So helicity density would be A dot B, so vector potential times magnetic field. And the helicity density is a quantity that you can calculate at each pixel of the simulation. What we see is that, for example, if we again look at the colors, then, for example, a red here means positive, or you could say right-handed helicity if you want, and minus means exactly the other-handedness of the helicity. What we see is then the main loop here in the core, which is this field line again. This one is rooted actually in helicity that is positive at the base, but in the corona, the helicity along that field line is actually negative. So it's of opposite sign. And the other loop here in the core that did not really develop to a loop, that is actually rooted in purely blue, so negative helicity. And in the corona, if you check carefully, that is also blue. Light blue, I would say. So not very negative, but not positive at least. So there's no sign reversal along this other loop. So that is quite interesting because it shows us that this loop, which is heated strongest in the corona, is actually undergoing a sign reversal of helicity from lower areas in the corona to higher up. And then, of course, the question is if that is a consistent trend in the whole volume, or if that is only a feature along that particular loop or this field line. So yes, so we can check a bit further. Yes, problem I should maybe mention. So the magnetic helicity density, so A dot B, that is unfortunately depending on the gauge of A. So you can choose any A to reproduce this B, but with a different gauge. And that would mean the helicity density is actually different because it is from a different A, right? So that means the helicity density here is depending on the gauge, and it's not a unique quantity, right? So if you choose a different gauge, you may have a different output. So that's, of course, not good for what I just said. So, but on the other hand, what we can do, we can construct a new quantity, which is the relative magnetic helicity. In this case, that would be a quantity that we define, let's say, above the photosphere, let's say in a half volume, which is half infinite. Yes. So, and then, of course, what we should do then is, if we start from one layer Z, we do an integration up to infinity, and in horizontal direction also in infinity. Then this quantity is defined like so. So you have the actual vector potential A, and then you add the vector potential of a potential field that matches the surface layer, right? So you take the surface layer, compute a potential field, and then you take A plus A pot, so that would be a new quantity, and then you you multiply with B minus B pot. So you subtract the potential field from the actual magnetic field, And if you do this volume integral, you get out a new quantity, and it turns out this quantity is independent of the gauge. So if you change the gauge of A, which may of course happen in a simulation, or theoretically, or anyway, that quantity is always the same. And interestingly, for our simulation, we can do that because our box is horizontally periodic. So if you take the volume integral, that actually is an integral from -infinity to +infinity, because periodic things do continue. And well, for the infinity, for the top, there we just have to cut off where there is the end of the box, so to say. That is, yeah, something that we cannot avoid because we don't have data outside of the top. But okay, so in principle, this gives us a quantity that is independent of the gauge. And yes, what we can then do in principle also is we can separate two parts from here. I will maybe show the consequences of that later. So the relative magnetic helicity can be separated into one part, which is the potential part, and a second part, which is then the non-potential, so the current carrying helicity and the potential current helicity. And they are defined in these two ways, as you see here. So again, using a potential field extrapolation from the same surface layer, and you construct these quantities like this. And it turns out, if you do the math correctly, it's mainly an exercise for meditation, I would say. You will find that is the same quantity, and this separation can actually be used. So now let's have a look at the relative magnetic helicity. Unfortunately, this is only defined on the volume. So we cannot now check, let's say, each pixel in the simulation, but we can check different volumes. And what you can do is, of course, you take the surface layer Z here with Z equals 0, which is the photosphere, and you do the same computation with another potential field extrapolation from a different layer, which is a little bit higher up, for example. You compute the same quantity again. And then what you can do is you can subtract these two volumes from each other, right? And what remains is then the relative helicity in a thin layer with height, so to say, in this thin layer from the photosphere to maybe 1 megameter above. And you can construct each of these quantities for each layer in the simulation by subtracting, let's say, this integral from Z to infinity and the same integral from Z plus delta Z to infinity, right? And that gives you then the relative helicity in each layer in each height. And that is what we plot here. So vertical is the height, and horizontal is the relative helicity in each XY layer. And then what you find is, if you look at the magnetic relative helicity, that below here, there is clearly a positive sign, right? But if we go to, for example, here above 5.5 megameters, there the sign of the helicity seems to reverse, as we have seen it with the loop. And in the corona, we have predominating a negative sign. And then this goes close to 0, of course, because if you go to the top of the simulation domain, everything becomes very potential and less braided, and there's not much helicity left. So, okay, so that would be the shape of the magnetic relative helicity. Now let's compare that with the same quantity, but gauge dependent. So that is our helicity density, which I plot here as HM. So we also average that in each height layer. And then you see this is the dotted line, and it pretty much follows the red line, which means it seems, of course, there's some difference between it, which might be due to changes, local changes due to changes in the gauge of A, but the general trend is conserved. So that makes us confident that the plotting of the helicity density was at least not totally wrong. And okay, so we have a clear coincidence between magnetic helicity density and relative magnetic helicity density. On the other hand, you can also plot the current carrying helicity density. So that is what you would plot here, like the same integrals, but instead of A dot B, you take B dot J, right? So that is what we call current helicity. And then you see that also has a negative component down here, then it has a positive sign. And then above 13 megameters, you see again, it is negative. So there seems to be also a sign reversal, but at different places. So, okay, So that seems to be consistent with what we have seen in the above the active region. Now we can actually separate, sorry, we can separate the two parts, the active region part and the quiet sun part. So the full field of view is the same as I've shown you, just with a larger amplitude here. The black color is the same as you have seen before. This is the magnetic relative helicity. And that is, you see, there's the sign reversal. We get the sign reversal around 9 megameters, or sorry, 5 megameters. And now we separate the quiet sun part from the active region part. So that is the blue dashed line and the orange dotted line. You see the quiet sun part has no sign reversal. But the active region part, that has a sign reversal. And if you restrict to that volume, the amplitude here is even stronger. So the significance is even improved. And then to the right side, well, of course, you can say magnetic fields are very, very weak here in the upper part. So it might be that we don't see other sign reversals there. So we can actually normalize with the magnetic field squared. So that would be the relative helicity density divided by magnetic field squared, or flux density squared. And then we see, of course, then the amplitude is less because the magnetic field is strong for the active region. Then the amplitude, of course, is less, but the general trend is still conserved. So, and for the upper part of the box, we don't reach zero, of course, because magnetic fields are weak. So that means the amplitude is improved here and it's reduced here, but the general trend is still there. And in particular for the quiet sun, we see there's only one sign of helicity. And we must say also that what you see here in the quiet sun must, of course, exactly compensate what is non-zero total helicity in the active region part. So these two parts do complement each other. So the quiet sun here is just balancing out in this case. Okay. So then we want to know, of course, if that is a general feature on large scales or on small scales or in all scales. So what we can do is, what I plot for you here is, again, the helicity density. So the gauge depending quantity, but we see it, well, at least the sign reversal should be present, as we have proven, at different heights. So the uppermost line here, that corresponds to about 2 megameters. So that is slightly above the photosphere. Then we have next to the sign reversals at about 5 megameters, and then at 13 megameters where the sign should have already reversed. And on the left column, so on the left columns here, you see the magnetic helicity density. On the right columns, it's the current helicity. So for the magnetic helicity density, there we see that for certain scales, and that means large spatial scales are on the right end of the spectrum. So you see here the K vector, that is because this is a spectrum of the helicity density. And small scales are actually on the left side here. So there we see that for the large scales, there we have, for example, blue handedness or negative helicity. And near the sign reversal, that is still the case. But if we go above the sign reversal height, then we see all these large scales are actually red, except some few dots maybe. So you clearly see the sign reversal is present on large spatial scales, but also it looks like, for example, if we look at smaller spatial scales, we have blue here, red here, and red here. So there seems also to be a sign reversal in smaller spatial scales. And for the very small spatial scales, well, that could be an effect of random fashion, right? So if you look at the very small scales here, it looks very random. So what you see actually with these many dots, that is the imprint of the granulation on the field at 1.8 megameters height. And you see also the granulation either, well, I don't want to say it disappeared, but because the field is expanding in the corona, that leads to a smearing out of the granulations. Some do not even connect to the corona, and some have a large impact on the corona. So that really depends on each individual granule. But you don't see that direct imprint in the same spatial scale, at least from the granulation, once you reach 5 megameters. The same roughly is true also for the, so you can see the same trends in the current helicity that we have seen in the other plot also. So If you look, for example, here, there's mainly blue. If we go above the sign reversal, there's mainly red. If we go too high, then current helicity becomes already weak. And well, it could be that there's some random switching of color, but yes. Okay. So now back to the question, how braided is the field and what is the connectivity of the magnetic field? So the topology. So here I show you a plot where I made, so to say, a ribbon. And I should maybe say, so that is one polarity on the left side here, and the other large polarity was on the right side. This ribbon basically goes horizontally across the central loop that we have found. And then we follow that ribbon of streamlines back to the surface, right? And that is what comes out with these many colored lines. What do we see? Well, mainly the expanding of the field is not extremely large. So if you look the thickness of this ribbon here down here, it is maybe only half of the thick or the width of the ribbon in the corona. And if you go to the other end, we have a similar behavior. So the width of the ribbon is smaller, but not extremely small. So if you took, for example, the scale of the pressure, the scale height of the pressure, you would expect a larger expansion of the field in the corona if there would be no field around it. So if you had just two polarities and nothing else, then you would expect a large spreading of the magnetic field in the corona. But in this case, this active region seems to be the magnetic field is confined from the outside field, and therefore the expansion of the field towards the corona is not so extreme, at least for this loop in the core here. That is, of course, different from magnetic field further out. Yeah? So there the spreading does exist, but here, for this particular loop, it seems the field is more confined. And that actually rises the flux density around the core of this loop, or around this loop in the core. Okay, what we also see is an interesting feature. This ribbon that is actually straight on one end is actually folded on the other hand. Yeah, so that means in between here, between the two ends of the loop, there is indeed some kind of twisting or folding of magnetic field lines or entangling of magnetic field lines. But if you consider the amount of twist, that means along that whole loop, which is about maybe 50 megameters long or 80 megameters long, along this loop, the braiding is so small, at least in the corona, that the winding number along the loop is maybe on 100 megameters about 1/3. Yeah, so that means the magnetic field is not like Parker suggested, like totally wound around each other, and then you have large reconnection events and short-lived reconnection events. But what we do see in our model, at least, is there is some small amount of twist. And that, of course, leads to some very tiny shear in the magnetic field, but that still can be diffused, right? So since you have a diffusion equation, it will act on any derivative, no matter how small it is, and it will convert magnetic energy to heat. And in particular, along this loop, we see the field is indeed not totally braided in the corona, right? So that model view seems to be needs to be revised a little bit. And then we can discuss here the small loops at the periphery, where you remember here, we enter the lower atmosphere. So that is the coronal part, and here is the chromospheric part of the field. So what is very interesting, if you look in the chromosphere, you see a lot of these field lines, they actually seem to go one over the other, right? So that is anytime one color crosses the other color, like for example here, that indicates that there's a lot more twist and braiding in the magnetic field at the chromospheric level. And that can also be explained. So when the field is quite parallel in the corona, that is only, I would say, a consequence of the much higher Alfvén travel speed in the corona as compared to the lower atmosphere. So when you start braiding a field from the photosphere, you may have a braided field in the chromosphere, but these perturbances, they travel along the field with a certain speed, which is low, maybe 10 to 100 times lower than in the corona. But once this disturbance reach the corona, the disturbance travel very quickly, along the field in the corona, and then that implicitly means that you could say the entangling can actually not work in the corona correctly. So if you try to entangle from a low Alfvén speed region, the amount of twist that you can cause in the corona is only very little. Yeah, because the disturbance travels very quickly to the other end, and then it will lead to, again, twist in the lower atmospheric layers.
Philip, you have 2 minutes.
Yes, okay. Yeah, this is just one of these loops shown from the side here. Plasma beta, maybe we can discuss that quickly. We checked that plasma beta is how does it change with height in the corona, and there's, I think, an important finding. So the original paper, which is cited, I think, already around 500 times, is Gary 2001. So this is a magnetic field extrapolation, actually, that was stretched to fit some observation in the solar wind or outer corona, I would say, so at 1,000 megameters distance. And that corresponds only to sunspot magnetic field. Yeah, and then they have a minimum maximum estimate here, which is the dotted black lines. And then there was this observation from EY at 2014, was a radio observation of the corona, and they found, oh, we do not match in the value range here. So they thought they made something wrong, maybe. And so what we checked then is in the model, you have, of course, you can compute plasma beta and compute the value ranges, in particular for active region case and quiet sun case. And we found that the active region value range and quiet sun value range is actually much larger than initially thought. And that means that this observation nicely fits, easily fits in the data that we have from the MHD simulation. And what is also particularly remarkable is that if you took the quiet sun and then take the maximum beta, you see that is the orange dotted line, you would find at practically any height, you would find values larger than 1. And that is, I think, surprising to some people, because I must say there are many works that assume that plasma beta is strictly smaller than 1 in the corona, and that is, of course, not true, as we see here, at least for the quiet sun part. In the active region, it is true for some extent in the corona, but this amount where plasma beta is smaller than 1 compared to Gary et al.'s work, this region is much less than what you could assume from this previous works. Okay, good. So then I'm open for questions.
Okay, thanks, Philip, for this nice talk. So we have some time for a few questions. I already see Axel. Yeah, Axel, you're unmuted.
I realize, yes, thanks very much. I have to, first a comment. I realized in the meantime that the relative velocity is actually not additive, and which is a bit of a problem, because we assume that we can simply calculate the relative velocity in one chunk by subtracting the two relative velocities between two different heights. So that is not completely rigorous because of the non-additivity. Another comment is now about the densities that you use. So what is the lowest density in your models? And what is the density where you typically see the sign reversal? Yes.
You mean the plasma density?
Yes.
Well, yes, I don't have the plot in here, but the plasma density that we use is like, I took 3 types of stratifications of the solar atmosphere, of the interior, of the lower atmosphere, and of the corona. So that is consistent with observations, roughly. But the density, honestly, it varies by at least 1 order of magnitude. Depends on.
So what is the lowest then? Lowest value?
Oh, I have to look it up if you want. I don't know by heart, but I guess it's something,
is it something like 10 to the minus 11 or more like 10 to the minus 16 already?
If I have it in SI units, so that is per cubic meter, it is something like 10 to the minus 15 sometimes, which is very low. So if you want to, I mean, particles per.
No, I want grams per cubic centimeter, but that's
yes, CGS, yes, I know.
Magnitude.
Okay, I will convert that for you if you want. Yes.
Which is so it's actually it's actually 10 to the minus 18 then.
No, wait. No, wait, that's 10 to the minus 15. Sorry, that is CGS because my unit system is different. No, that's 10 to the minus 15. Yes.
In CGS.
Yes, I guess.
Yeah.
Yes.
And
I
then,
will check it
and
once
then
more.
if the temperatures would be around 10 to the 6, right?
Yes, it can be up to 1.5 million Kelvin. Yes, easily.
And then that actually means that the magnetic Prandtl number is actually large. Okay, so I will check that again. So you say 10 to the minus 15, right? Yes.
Yes.
And so then the magnetic Prandtl number is actually what is my cursor? Yeah, 10 to the 10. So that's really big, and that means that most of if you go back to one of your early plots in the Bingert plot.
Which plot?
Bingert plot, the Bingert plot about the yeah, right, that one. That actually means that most of the energy must actually be dissipated viscously, because in reality the magnetic Prandtl number is very large.
Yes. Well, in the model, what we have is our viscosity is exactly the same as the eta. Yeah.
Yes, but in reality, is of course not. And we know what it means, namely that most of the dissipation must be viscous dissipation. Then.
I don't fully agree. The reason is, so what we do in the model is we adapt, of course. So our resistivity is not the realistic one, but our viscosity is the realistic one. So what we do is with the fluid description, with a higher resistivity eta, we adapt the dissipation to a different length scale. So that is the basic thing you do when you change the resistivity. You adapt to the length scale of our grid. And that would mean if you go now to realistic values, in reality, the dissipation of the magnetic energy is just on smaller scales, which means on electronic scales, which is totally expected. And if you compare electronic scales with our grid scale, you will see if you scale the eta accordingly, that comes about the realistic eta. So I'm not sure if that really tells us that the dissipation must be viscous. Actually, I think not, because when you go to smaller scales in the dissipation, what happens is the amount of energy that you dissipate within a given volume just rises, because the total energy dissipation in a volume is always the same. If you pump the same magnetic energy into it, and a current sheet is either large or small, what I think, or personally I'm convinced, is that the amplitude of the current sheet just changes because you pump the same energy, right?
So I think it would be good to readdress that. There is this paper by myself and Matthias Rempel of 2019.
Yes, okay.
You know that paper?
Yeah, okay.
Yeah, I think you can also discuss it on Slack.
Yes.
Good idea, yeah.
Yeah, so Jennifer, just quick question, Jennifer.
Yes, thanks. I had a question, maybe you mentioned it, which gauge were you using in the simulation? And I was wondering, in this plot where you showed the helicity as a function of height, the relative helicity and the normal helicity, they were like pretty close, but I was wondering how the magnetic helicity would look like in a different gauge. Did you investigate that?
Yeah, no, we cannot investigate a different gauge simply because it would mean we have to rerun the simulation.
Yes.
With a different gauge, which it costs maybe a year of computing time.
Oh, it's a year, okay.
Yes.
And which gauge did you use here?
Yes, the gauge is implicitly set through the potential field extrapolation at the bottom. And that is, if I remember correctly, the Lorentz gauge. So that should set the gauge at the bottom, the horizontal domain. So the horizontal the horizontal boundaries are periodic. That means that cannot change the gauge. And then on top, we have again a potential field extrapolation, again with a gauge, which is the Lorentz gauge. And that means, for me, it means it's fixed. Of course, there could be small variations within the box, maybe, that I'm not perfectly sure. Maybe Axel, that is a theoretical question. If we set the gauge at all non-periodic boundaries to be the Lorentz gauge, can the gauge within the volume change then?
No, I don't think so. I think that's
Yeah.
unfixed.
Mhm.
One
Yeah,
should really think of the velocity, the magnetic vector potential really as a velocity.
Axel,
So if you think of A as being a velocity, then the velocity field is completely fixed by the boundary conditions. If somebody gave you just a vorticity plus a boundary condition for the velocity, then you can always calculate the full velocity from the vorticity.
Axel, I think